Okay, this is 2012, and this is number 6. This is the second time they've kind of referenced Taylor series in this year. Um, they give us actually a lot of information. They tell us that G has derivative of all orders, and it gives us this, and it even tells us the first three terms. Again, it doesn't have to tell you the first three terms. I'm not actually sure why they do. It makes this question a little easier, but again, to get these terms, it is just plugging in n equals to 0 for that guy, n equals to 1, and n equals to 2, plus dot, 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 dot. You get as much as you want. You can see it's an alternating series. It's going to go up by odd powers, and then the denominator is going to start at 3. That's what that plus 3 does instead of a plus 1, but it's still going to be odd, right? 2n plus 3 is odd, just like 2n plus 1 is odd. It's just shifted out, right? This is a 1 and a 3 and a 3 and a 5, because 2n plus 1 is 2 less than 2n plus 3. Okay, and they're going to ask us questions. I actually think this one is one of the easier ones. There's not too many confusing things. It does have an error question in it, but I like how it's worded. It's not too bad. I'll bring this back down here after we do part A. Part A is kind of the basic one where it says find the interval of convergence. So we find the interval of convergence using the ratio test. The ratio test looks at the limit of a to the n plus 1 over a to the n as n goes to infinity. Right, anytime you want to find the interval of something, or you want to find the radius of convergence, you're going to do the ratio test. And the ratio test is just looking at this limit. So I can add 1 to everything. Again, if you want to, you can just ignore this. We talked about this in a previous video. If you look at the ratio of an alternating series, of course you're just going to get a negative, but that negative doesn't matter. Remember, when we look at the ratio test, we're always going to set that limit in between -1 and 1. Whether that limit is a negative or a positive, it's still the same thing setting in between -1 and 1. So I'm not going to look at that. Okay? I'm going to add 1. Adding 1 to n, you have to be careful. I won't skip this step, but you got to add it like this. You got to be careful in how you add these, and this is just the same original function. Okay, now think about what this is. This is x. That's 2n plus 2, so that's 2n plus 3 all over, that's going to be 2n plus 2 plus 3, 2n plus 5 all over x to the 2n plus 1 over 2n plus 3. Now, as n goes to infinity, 2n plus 5 and 2n plus 3 are the same thing. This is 2n plus 3, 2n plus 1. That's an extra 2 factors of x squared. So when it's all said and done, you're going to do that. And again, setting x squared in there, well, x squared can't even be less than that. So we don't have to worry about that, right? X squared is clearly always greater than that. But when you solve for x and you take the square root, well, when you take the square root, you introduce the plus or minus anyways, and you still get that same thing. Again, hopefully you're okay with the fact that if x squared is less than 1, that is the same thing as saying this. Okay, now we're not done. We have to check the endpoints. Endpoints. Don't forget to check the endpoints, right? That's not the full interval yet. That's just what the ratio test gives us, and now we need to look. So when you look, if x is 1, or if x is -1, right? You have to check both endpoints, then you have to decide. Okay, so come up here, and let's make x equal to 1. Okay, if x is equal to 1, 1 to the 2n plus 1, well, that's just 1. And so x equals to 1 gives us the alternating series 1 over 2n plus 3. And we know that the alternating version of like a 1 over n is okay. So we want to make that, include that. And if we look at -1, we get -1 to the n, -1 to the 2n plus 1, okay, all over 2n plus 3. And you have to really think about what all this is. -1 to the n, -1 to the 2n plus 1, you would add exponents, and you would get -1 to the 3n plus 1 all over 2n plus 3. Okay, just be careful with this. This is like -1 to the n, -1 to a different stuff. Those two are exponents of the same base. You would add them together to get 3n plus 1. And you have to think about 3n plus 1. Does that make this alternate? And it does. Okay, when n equals to 1, this would end up being a 4. When n equals to 2, this is a 7. When n equals to 3, it's a 10. When n equals to 4, it's a 13. See how it's still going even, odd, even, odd, even, odd? Which means the negative 1 makes this thing alternate. So the alternating version, again, of 1 over 2n plus 3 also works. And so there's your interval of convergence. As a reminder, the interval of convergence, we always do the ratio test. The ratio test limit we want between negative 1 and 1, and then we have to check the endpoints. Unless the original function was just geometric, then we don't have to check the endpoints because we know they don't work. Otherwise, we need to, and it's not geometric because this 2n plus 3 makes it non-geometric. Both endpoints work in this case because both endpoints make the corresponding series an alternating 1 over n, and both of those then converge. Okay, I'm going to bring part B down here again, and let's take a look at it. Okay, part B. Part B says, the Maclaurin series for G, evaluated at 1/2, is an alternating series whose terms decrease in absolute value to 0, meaning it's a decreasing function. Basically, it's reminding you that it's an alternating series, and so if we know that it's an alternating series, the error is just the next term. Okay? The approximation for G of 1 using the first two non-zero terms of this choice is 1 over 17. Okay? Show that this approximation differs from the real value by less than 1 over 200. And again, think about what that's saying. All this is saying is show that the error is less than or equal to 1 over 200 using the first two non-zero terms. So, if we use the first two terms, what's the error? Bingo, that guy. So all this is saying, I know that's a lot of words, it tells you it's alternating. So we know we can use the next term. It says if we use the first two non-zero terms, show that the approximation differs, meaning the error, is less than 1 over 200. We know that the error is this circle right here. So all we have to show is that that guy is less than that. So the only thing you have to really say is, on part B, is that you know that the difference between the function's value and this approximation, right, that's the actual error, is less than this guy, 1/2 to the 5th over 7 is equal to 1 over 224, and bingo, we've shown that the error is less than 1 over 200. Okay, we just showed that the error is less than 1 over 224. 1 over 224 is what this is when x is 1/2, and we know that if we're using these two for our function, and it's an alternating series, that the error is the next term. Okay? Okay, and then part C isn't too bad. Part C just wants you to find G prime. But G prime is pretty easy. Certainly the first three terms, they gave you right here, right? They gave you the first three terms of G, so just take those derivatives. So the derivative is 1/3. The derivative here is negative 3/5 x squared. The derivative here is 5/7 x to the 4th. So that's the easy part. And then the general term plus ... Well, then you just take the derivative of this guy. Okay, the derivative there. The alternating part doesn't do anything. And then take the derivative, bring the power down, decrease the power by 1, and then this 2n plus 3 just chills. And then you're good. Everything makes sense here? Ratio test to find the interval of convergence. Analyze the endpoints, looking at specifically what happens when x is 1 and when x is -1. This, we wanted to show that the error is the difference between the function and the approximation, is less than the upper bound estimate. For an alternating series, the error term is just the next term that you didn't use. In the problem, it tells us to use the first two terms as our polynomial, so then the next term is our error. We just need to show that that term is less than 1 over 200. You can show that it's equal to 1 over 224. Bingo, we're good then. These have an error less than 1 over 200. Part C just wanted us to find a series for g prime. This is equal to g. So we just take these three derivatives to find the first three terms, and then we can take the derivative of the abstract or the general term to find this. Remember, when you're taking a derivative, don't worry about this. Don't worry about this. You're taking the derivative with respect to x. So just do power rule. Bring the power down, decrease the power by 1. That's all I did. Bring 2n plus 1 down, decrease the power by 1, chill, chill, and now I have the first three non-zero terms and the general term for the derivative.